Hello and welcome to this 7th session where we're going to be looking at helium in particular, really focusing on the spin of the electrons and spin in general. So you can actually see in this picture here we've got our helium lamp going, and in that top photo of the helium lamp you might be able to see that just nearby, clamped up, is just a very small little spectroscope, and through that spectroscope we took the picture below, which it's not the clearest picture, but essentially it does show there are some lines there in the spectrum. Now, we're familiar with the hydrogen line spectrum, which is really very regular and simple and organized in its appearance. And that hydrogen spectrum is completely understood without any reference to electron spin. All we refer to in that spectrum are the shells which the electron moves between. And in fact, one of the amazing things we often forget is the Schrödinger equation doesn't even predict electron spin, weirdly. But curiously, the helium spectrum, which is quite a lot more complicated, simply cannot be understood without spin. Obviously, it's a 2-electron atom now. And so Niels Bohr, who in his 1913 theory of electron shells really completely explained the hydrogen spectrum, Bohr did really struggle with helium. Helium really couldn't be explained using Niels Bohr's methods. And in fact, Niels Bohr gave an equation, sorry, I beg your pardon, he was giving a lecture when he was describing the problems he was having with helium. And it's curious that Wolfgang Pauli was in the audience of that lecture. And it was Pauli who ultimately managed to solve the problem of helium. And it was really his genius to work out how it all came down to electron spin. So in fact, of course, really that there was no concept of electron spin by Schrödinger when he looked at the hydrogen atom, because spin wasn't necessary to solve it. And so it was really the genius of Pauli that made him realize there was something else that must be intrinsic to the electrons that's going to be required to solve the helium spectrum. And so not only is spin something to be understood when you're trying to understand the helium spectrum, but to make life even more complicated, we can't really just get away with considering the electrons in isolation all the time, as is so kind of tempting and intuitive to do in chemistry. But actually we need to kind of couple them together to give a product, a resultant wave function. And this is certainly important with spectroscopy, with interactions with light. And the way I like to think about this is that the atom is actually minuscule compared to the wavelength of light, certainly visible light and ultraviolet light. So if you like, you can almost imagine it as the light travelling along. The atom is just like a speck to the light, so the light almost can't see the inner workings of the atom. It just sees the whole atom wave function, and so it effectively will interact with the sort of coupled product of all the angular momenta that are going on inside the atom. So we've got two types of angular momentum now. We've got the orbital angular momentum that we get from the subshells and the orbitals, and of course the intrinsic spin angular momentum as well. We've got two types of angular momentum associated with each electron, and we've got multiple electrons where these angular momenta all need to be added up and combined as vectors. And so as we've seen before with addition of vectors, if you've got vectors of length L1 and L2, then the longest possible resultant when the vectors sort of add directly together would be L1 plus L2, and likewise if they're pointing in opposite directions, then you'd be looking at the difference between those two vectors. And when you're looking at just the length of the vector as a magnitude, we always consider it as a positive value, which is why we've got those vertical lines, those modulus lines. And as we've seen before, when we're looking at these discrete quantum systems, we're always looking at integer jumps between quantum numbers. So if we have L1 plus L2 as a max and L1 minus L2 as a minimum, then we can move between those only in integer steps. And in fact, before we go any further, one thing I wanted to mention to you is a curiosity to do with full subshells. And so we're used to seeing these electrons in boxes notation that we can see on the screen. And so effectively within a subshell, for example the p subshell, we can think of the the boxes in which the electrons occupy. We can think of these as carrying information about the ML quantum number, which is this projection of the orbital angular momentum. And the electron spin there, which is shown pointing up or pointing down, these are the two orientations of the spin. These are the m sub s quantum number. We can think of it as plus half for spin up and minus a half for spin down. But it's quite interesting, when you look at the whole P6 subshell there, which is completely full, when we add up all these values of ms and ml, you can see that all the ml's have to add up to 0, because we're occupying plus 1, 0 and minus 1, if you like, mLs, or 2 times over, with both up and down electrons included. And so all those plus 1s, noughts and minus 1s will cancel to 0. And so the sum of all the mLs, which is denoted with capital letters, which is what we use for multi-electron states, capital M sub L, will equal 0. And likewise, when we're considering the spin states, the plus half and minus a half for the m sub s, of course when you add these all together, because we've got equal numbers of up and down electrons, they also combine to give 0. And so putting it in capital letters now, capital M sub s equals 0. And so once we work out this resultant then, in terms of the projection of the angular momentum, we then ask ourselves, what must be the parent capital L and the parent capital S vectors which give us these projections of 0? And since there's no other way of arranging 6 electrons in a p subshell, it means that the ms equals 0 and ml equals 0 are the only possible values we can have for these quantum numbers, and so that implies that the parent vectors are capital L equals 0 and capital S equals 0. This is very interesting because, of course, we see then, looking at this whole subshell, this full subshell actually has overall no angular momentum of any type, neither orbital nor spin. And that's quite curious because it shows then that the full subshell is kind of invisible from the point of view of angular momentum. It's no different to a completely empty subshell. And that's why, in a sense, spectroscopically, full and empty subshells have quite a bit in common. And also, as you can imagine, like the core shells in an atom, again, because they're all involved full shells and subshells, these are, in a sense, invisible. And these actually make atomic spectra much simpler, when you only really have to consider the so-called open shells or subshells, where you have a partially full subshell. Now, onto the helium spectrum itself. Very curious spectrum, helium. And you can see on the diagram there, on the right-hand side, that we have what appears to be 2 sets of levels, labelled singlet levels on the left and triplet levels on the right. And the fine dotted lines there represent possible transitions between levels. And the curious thing about this picture is that there are no transitions between the 2 sets of levels. So we've just got transitions within the singlets on the left, transitions within the triplets on the right. And so it does actually look like, 2, if you like, separate species, 2 separate spectra. And so in fact, early chemists, when they first analysed the spectrum, they thought there must be just 2 different types of helium, which were initially called para and ortho helium. And there was some effort to separate helium into these 2 species, but of course nobody ever managed it. And so you're looking at these singlet and triplet levels. These actually are referenced to the capital S total spin quantum number. So if capital S equals 0, this implies that the electrons are anti-parallel, so 1 up, 1 down. So the spins plus half and minus a half add up to 0. So you've got the anti-parallel electrons. And so the capital S equals 1 is described as triplet. So the word triplet implies capital S equals 1. And so this is for 2 electrons spinning parallel with one another. So you can see that in these pictures on the right hand side there, we don't see the 1s level. And that's because the 1s is a lot lower down, and it would sort of muck up the scale if we had the 1s in there as well. But you can see on the singlet levels, we've got this dotted line going down towards 1s. We just don't see the actual 1s. And so what this implies, the fact that these two spectra appear separate, is that light cannot flip the spin. Because to get from a singlet level to a triplet level, clearly you can imagine one of the electrons would have to have its spin flipped. So if the singlets are like one spin up and the other spin down, we'd have to maybe flip the down to up. So you can have two parallel up electrons, for example, which you might describe as a triplet state. So that's quite an interesting thing in itself, that light can't flip the spin. Now, looking at these diagrams in a bit more detail, I didn't mention before the so-called term symbols. So these are right at the top here. So you can see the capital S, P, D and F, and they've got these superscripted numbers, and they're all 1s for singlets, and they're all 3s for triplets. And so, in fact, what this number means, it's the so-called multiplicity of the spin, which means the number of possible spin states or projections of that spin angular momentum. So if the capital S equals 0, there's obviously just there's only the 0 state. There's only one projection of that spin, and that's where the origin of the 1 is, in the superscripted 1. Whereas with the triplet levels, if the spin vector is, if you like, length 1, then there are 3 possible projections of that, plus 1, 0, and minus 1. And so we'd say the spin multiplicity is 3, hence the 3 being the superscript. And of course this is the origin of the word triplet. So this is all just kind of spectroscopic notation. So there we go, spin degeneracy, 2s plus 1 in general, or 2 times any angular momentum plus 1 are the total number of states. And then one thing to bear in mind is that the capital letter there, as we mentioned before with the P6 full subshell, the capital letters denote the multi-electron state. But of course, in both of these pictures, of the 2 electrons in helium, one of the electrons remains in the 1s orbital, which is not shown, and it's the second electron which is excited up to one of these higher levels. And so, since the electron that's remained behind is in an s state, where the angular momentum is 0, it means that the total angular momentum of the atom in each case is simply given by the excited electron. And that's why you can see the sp, d and f are simply lined up with the sp, d and f atomic orbitals there in the picture. So there you go, the capital letter means we've added the angular momentum together, but of course one of them was 0 anyway, because of the electron in the 1s orbital. So there are a few things to say about the difference from hydrogen, and perhaps the first thing to say is that the subshells in these diagrams are not all the same energy. And this is one of the slightly surprising features we see in the hydrogen spectrum, is that all the subshells appear at the same energy within a given shell. And we rationalise this by saying that there's only one electron in hydrogen, and we see the different subshell energies as evidence of shielding, because the orbitals of the different subshells are different shapes. Then they interact slightly differently in a multi-electron atom with other electrons. Hence the shielding will depend on in which subshell the other electron is in. So when we've got a multi-electron atom, the energy levels of the subshells are in general going to be different. Hence they're not all just lined up neatly like in hydrogen there. And then, as we said before, we've got one of the electrons in the 1s orbital, while the second electron is excited up to one of the levels in the picture. And one thing that's curious here is that when you consider the triplet levels, you see because there's no dotted line going down, that implies that the 1s electron not shown and the 2s excited electron there in that bottom state, that will be the ground state from the triplet, as it were, spectrum. Whereas in the singlet spectrum, we see there's a dotted line that takes us down from 2p down to the unwritten 1s on the left-hand side. So in fact, the ground state of singlet levels will just be 1s2. But when it comes to the triplet, the ground state is 1s1, 2s1, and we think of this as being a reflection of the Pauli principle, which would forbid a 1s2 triplet state, which would imply both electrons in the 1s orbital, but both spinning in the same direction. And so this is going to take us on to talk a little bit about the Pauli principle. So the Pauli principle, so chemists typically think of the Pauli principle as meaning that you can't have two electrons in an atom which have all the quantum numbers the same. So of course if you had two up electrons, for example, in a 1s orbital, all the quantum numbers would be the same. So you'd have L equals 0 and ML equals 0 if it's a 1s orbital. You'd have the shell quantum number would be equal to 1, and the ms would be the same if both the electrons were spin up. But the point I want to make now is that in a way the Pauli principle is much more general than this, much more broad than this. It doesn't even just apply to electrons, it actually applies to all spin half particles, and actually all components of matter, protons, neutrons and electrons, they are all spin half particles. And so they're called fermions, all of these spin half particles. And so this is something that's applicable to all fermions. And at a fundamental level, it's to do with this coupled wave function. And that is, if you exchange two particles, the coupled wave function has to change sign. So that might seem a bit sort of random and abstract, but we're going to see it does have big implications, because that, if you like, implies that the coupled wave function has a particular form. So for example, if you had a 1s2 in the singlet state, which is to say you've got an up electron and a down electron, then the psi here, which would be the coupled wave function for both electrons, if you like, if you build it up from the individual electron wave functions, which are these phi up arrow for the up electron, phi down arrow for the down electrons, it would imply this kind of arrangement that we've got here. So you can see it's phi up, phi down, minus phi down, phi up. And so you can see here that if we were just to switch the labels of the up arrow and the down arrow, see that first state there would turn into phi down, phi up, and the second half of it would be phi up, phi down. And so that would be, if you think about the minus sign in there, that would be exactly minus what it was in the first place. So that implies there that when you exchange the particles, you change the sign of the wave function. And so this is something which the Pauli principle demands, and so such a wave function is said to be antisymmetric. But of course you'd have a big problem, because if you try to set up the wave function in the same way for a triplet 1s2, where both electrons were spin up, for example, you'd have phi up minus phi up, phi up. And so this simply has to equal 0. Those two terms have to cancel out. So by equaling 0, the wave function, if you like, is vanishing. And so if the wave function vanishes, that's clearly not an acceptable state to have two electrons spinning up in the same orbital. And so that prohibits the wave function from existing. Now onto the helium spectrum. And so I've pulled up some details here I found of the spectrum. So on the left-hand column there, we've got the wavelength, lambda. And this is in the fairly old-fashioned unit of angstroms, where an angstrom is 10 to the minus 10 meters. So an angstrom is about the diameter of a hydrogen atom. And so there we go. We've got all these wavelengths are in the visible there, so they're all between sort of 400 and 750, so 4,000 and 7,500 angstroms rather. Those intensities there, I think that's just some arbitrary unit. And then we have these configurations. So they're written in the kind of spectroscopic language. So these are all emission lines, and so spectroscopists tend to write down the lowest energy level first, and then the arrows pointing right to left, where it's dropped down from the higher energy level on the right hand side. So you can see that when we look at these levels, we can see that all of them involve having a 1s electron, common to all of these levels. So it's just the second electron which has been excited. And so you can see that on the right hand side we've got that electron excited into the fourth shell, one of the subshells up there, and then it's dropped back down and it's dropped into the second shell. So you may think it's a bit odd that the electron hasn't excited perhaps all the way back to the first shell. And in actual fact, of course, if we were looking at a triplet configuration, which is actually what we've got in the top case, you wouldn't be able to have the electron drop back to the first shell, because you can't have 1s2 in a triplet state. But even with these singlet ones, so for example you can see in the second row and the fourth row, these are singlets, you might have expected those ones to drop down to 1s2. And the reason we don't see those dropping down to 1s2 is because here we're just limiting ourselves to the visible part of the spectrum. And of course the first shell is going to be a lot lower in energy than the second shell, and so there'll be a much bigger energy gap. And so actually these transitions are going to come out in the ultraviolet, so we're not going to see them in our spectroscope. And so looking at these LS levels in the right hand column, so I've already made reference to the fact that we've got these threes or ones as superscripted. And so again we see that transitions remain within triplet levels or within singlet levels, but never between a singlet and a triplet. And then the other thing that's interesting there is looking at the capital letters. And so you can see that all those capital letters, remember they refer, ultimately it's a bit like we have with the subshell letters S, P and D, relating to the angular momentum 0, 1 and 2. You can see in each case the total angular momentum differs by 1. We don't see a different number change, and that turns out to be quite significant because this is going to relate to the selection rules. And so, as we said before, light can't change the spin of an electron, so that implies that the total spin angular momentum can't be changing in one of these transitions. That's summarised in our delta S equals 0 selection rule. And then we've also got delta L equals plus or minus 1, and this implies that, I guess, a unit of angular momentum, orbital angular momentum, has to change. And actually this comes from the photon of light. So of course a photon of light carries a unit of angular momentum, and that has to combine with the angular momentum in the electron states. Vector adds to those. And one curiosity here is that the 5876 angstrom transition there, this is the signature from the sun, because of course helium was discovered in the sun, and this was the wavelength of light that was seen, one of the Fraunhofer lines, where we get that black line in the otherwise continuous spectrum from the sun, and this was that line that couldn't be identified in any known element on Earth, and hence a new element was postulated in the sun, of course helium, named after Helios for sun. So now I thought I'd mention to you a little paradox, and this is about the so-called 2s2 state of helium. So you might think that it might be you might think it was fairly easy just to prepare a 2s2 state of helium. You could just excite electrons up from the 1s to the 2s subshells using the appropriate frequency of light and get that state. But it turns out that we actually can't prepare the helium atom in the 2s2 state very easily, certainly not well enough to measure its energy reliably. And in fact we can appreciate this by looking at the actual energies involved. So actually if you look at the energy axis there on these spectra, well, first of all it's a bit curious because we're actually using the so-called wave number scale, so the number of waves per centimetre. So it's a very sort of unorthodox type of scale, but actually it's something that spectroscopists often use, the so-called wave number. And so we're really looking at thousands of wave numbers on that y-axis there. But the relevant fact here is that to ionise a helium atom, you're having to use nearly 200,000 wave numbers to ionise it. And so you can see on our picture here, we've defined 0 as the ionisation limit. So you can see here that we've got 2s, we've got the second shell, the third shell, the fourth shell, and they're converging. So when you get up to 0, that's, if you like, sort of infinitieth shell, where we're ionising electrons. But it's very significant that the first ionisation of helium is nearly 200,000 wave numbers, because when you look at it here, the 2s, for example, the 2s subshell, that's only 30-odd thousand wave numbers below the ionisation limit. So you can see that in order to excite a 1s electron up to the 2s level, you can think about it, it's a bit like the 1s level will be at about 200,000 wave numbers, which is going to be, miles off the bottom of the diagram there. And so I'm making the point that to get from the 1s level up to the 2s, you're actually using over 3/4 of the first ionisation energy. So it's like you're going from, it's like minus 200,000 wave numbers up to sort of minus 30-odd thousand wave numbers. So using over 3/4 of the ionization energy to get 1 electron from the 1s subshell to the 2s subshell. And it's actually quite interesting, this thing about 3/4, because if you compare to the hydrogen atom, we had this very simple expression for the energy of an electron in hydrogen, where it's just minus the Rydberg constant, which is the ionization energy of hydrogen, divided by n squared, where n is the shell number. And so when the electron's in the first shell, the energy of the electron is minus the Rydberg, or minus the ionization energy. When the electron's in the second shell, it's minus the ionization energy over 4. So that's 2 squared. And so the difference between minus the Rydberg and minus the Rydberg over 4 is 3/4 of the Rydberg, 3/4 of the ionization energy. So you can see that the helium atom is not massively different to the hydrogen atom. So in fact, you've got to go 3/4 of the way from the ground state up to the ionization limit to get from the first to the second shell of energy, which just shows how rapidly that you get this convergence of energies. And so this is it, you see, because if you require 3/4 of the ionization energy to promote a single electron from 1s to 2s, then you would need about 1.5 times the ionization energy to promote both electrons from 1s to 2s. So this is the curious thing. Even though 2s2 looks like a kind of nice bound state of 2 electrons in the atom, it's actually much higher in energy than the ionization limit. So, this is a sort of paradox. So in fact, if you try and prepare the 2s2 state, because you're far above the ionization limit, then you'll find that the atom will just spontaneously ionize. So it's very difficult, as I say, to really work with these very high energy configurations. And so now I thought, I mean, this is slightly off topic, but I just thought it'd be quite interesting because we've spoken about ortho and para helium, the singlet and triplet states of helium. You may also have come across this idea of ortho and para hydrogen. Now this is a bit different because it's to do with H2, the molecule, and the ortho and para is to do with the nuclear states, not the electron states. But I couldn't resist mentioning this, also because ultimately it all boils down to spin, and spin is kind of the topic of today in the general sense. So I thought I'd mention about the hydrogen connection to helium. So as I said before, para helium, this is with the electron spins anti-parallel. And so the ground state for para helium will be 1s2, whereas the ground state for ortho helium, where the electrons are parallel with one another, will be 1s1, 2s1. So para is a lower energy state than ortho for helium. But when we look at hydrogen, ortho and para hydrogen, H2, so we're now looking at the proton spins. And of course a hydrogen atom has a nucleus of just 1 proton. And as we've seen, a proton is a spin half particle like an electron. It's another example of a fermion. So again, protons, like electrons, can be spin up or spin down. And so para hydrogen would be with the electrons, I beg your pardon, the 2 protons in the hydrogen molecule having opposite spins. So 1 spin up and 1 spin down. And we can see this in the picture here. So para hydrogen on the right there. And so this, as it turns out, is more stable than the ortho hydrogen where the protons are spin parallel. And so again, you can kind of appreciate this just considering them as kind of classical magnets. And so, not surprisingly, if you go to very, very low temperature, so there's very little thermal energy, ultimately the hydrogen is going to end up in its lowest energy state. So ultimately the hydrogen will end up as para hydrogen. And so this is indeed observed at very low temperature. But the really surprising thing is what happens at very high temperature. Because at very high temperature, when you've got loads of thermal energy, and so there's enough energy to knock these spins sort of up and down very easily. And so essentially what would happen is that all the spins would be kind of randomized. So you'd think there'd be equal probability of spin up and spin down. And so you would think at high temperature, you would get equal amounts of ortho and para hydrogen. So, think about the 4 possibilities, you've got up, up, down, down, and down, up. 2 of those you might consider to be ortho, the up, up and down, down, and 2 of those you might consider to be para, the down, up and the up, down. So it would appear, you'd think, that they're equally likely. Although slightly bizarrely, what we find, what's observed here, is that at high temperatures, when it's randomized, it's actually 3/4 ortho. How on earth do we explain this? And it actually comes down to what we spoke about before, to do with the fact that we don't consider these spins just as little independent things in isolation. Of course, they couple together, like all these kind of quantum particles do. They couple together to give a resultant. And so that's what we're going to see now. So here's our mystery, why don't we see 2 parallel and 2 anti-parallel spins? And the answer is we have to consider the resultants. So rather like we saw with 2 electrons in helium, they can spin together, spins parallel to give you s equals 1, or spins anti-parallel to give s equals 0. But the crucial thing here is, of course, is that when the electrons give you that capital S equals 1 state, you've actually got 3 possible components, 1, 0 and -1. Whereas when you consider the s equals 0 state, there's only one component, the ms equals 0. And so this is where the 3/4 ortho is going to come from. So you see, because we've got, as it were, 3 different ways of arranging s equals 1, and only one different way of arranging s equals 0, this is the like the 3/4 to 1/4 ratio between the 2 states. And so again, if you look at a wave function for the up and down wave functions of the proton spinning up and down, what we see there for s equals 0 is exactly what we saw for 1s2 in helium, where you've got a spin up, spin down, minus a spin down, spin up. So this is the so-called anti-symmetrized wave function, such that when you exchange the particles and you exchange those spins, the total wave function changes sign. But then we see something slightly odd happens when you look at the triplet state, because when the ms is equal to +1, you would think, well, that's just both spins up of the proton. When the ms equals -1, you'd think, well, that's just both spins down. But how can we explain ms equals 0 for a state where we're thinking the spins are parallel? This is the slightly kind of paradoxical thing about it. And this is what we've got here at the bottom of the screen. What you get when s equals 1, but its projection ms equals 0. And the answer is, it's rather like what we saw before, except we change the sign in the middle of the wave function. So it's phi up, phi down, plus phi down, phi up. But one of the problems with this is that we don't have an anti-symmetrized wave function any longer. So again, does that put a bit of a spanner in the works? And so getting slightly off topic now, but this does introduce some actually really interesting stuff, because of course Pauli's principle does require that we have an anti-symmetrized wave function, and this appears not to fit the bill. But the molecule has got other ways of kind of contriving an anti-symmetrized wave function, because really it's the wave function of the entire molecule that we need, as we kind of alluded to before, all these angular momentum and things all coupled together. And it turns out there's another type of property that these molecules have, and that is, of course, they rotate. And rotation is, like all other things really associated with molecules, apart from perhaps translation, rotation is another quantized phenomenon. So actually there'll be a rotational wave function as well. So the curious thing is that when hydrogen is in this triplet state, as it were, when we're looking at the ortho hydrogen, because the wave function for the spins of the protons, because that wave function is actually symmetric with respect to exchange of the particles of the protons, then it requires that the rotational wave function that describes the rotation of the molecule, that has to be antisymmetric. So it puts a restriction on the possible rotational states of the molecule. And this is quite historically interesting, because it turned out that hydrogen at very low temperatures really had bizarre thermal properties. So its heat capacity and things just was not supposed to be the kind of things that were observed. And it was to do with the fact that this whole question about symmetric versus antisymmetric wave functions was putting limitations on the rotational states of the molecule, and that was affecting the thermal capacity of hydrogen at very low temperature. So that's just a kind of interesting bit of history that just shows the kind of knock-on effects, the ramifications of these quite abstract bits of theory, things like, exchanges of particle, changing the signs of wave functions. Seems a bit like it's sort of made up, but it actually is affecting experimental results as well. And one thing which I just thought I'd add at the end is about spins coupling in the nucleus. This actually arose from a very good question that arose during the session. And so, of course, we're looking at electrons coupling with other electrons in the atom. Can we also see nuclear particles inside a nucleus doing a similar sort of thing? And the answer is yes. And it's very interesting. There's so much going on in the nucleus, and chemists don't normally consider what's going on inside the nucleus very much. Usually a chemist is just interested in the nuclear charge, as far as, that force that holds all the electrons in. I suppose chemists are interested in nuclear mass, because we need to know what atomic masses are in chemistry. But normally the business of things like the nuclear strong force is something we just leave to physicists. But actually another thing which about the nucleus turns out to be very significant in chemistry is nuclear spin. Because of course nuclear spin is the basis of the NMR experiment. Of course, we see proton NMR, carbon NMR. These are just dealing with nuclear spin states. And of course this relates to the fact that the nucleus is made up of protons and neutrons, and these are all spin half, and so these can all combine to the overall spin of the nucleus. So, chemists actually do have a certain amount of interest in spin coupling in the nucleus. So it's actually very curious and a bit odd what goes on, and we see the behaviour has got some things in common with electrons in shells and orbitals and things, and also some things that are different. So what they have in common actually is in the nucleus you do actually see shells like you do in an atom with the electron shells. So you can think of this, so there are shell quantum numbers, and indeed there are subshells. So it does mirror to some extent what you see in atoms, but actually it's not a so-called central field problem, which would be like electrons orbiting like a central point in the nucleus. So actually it's not identical, but there are certain parallels. And what it does have in common is we do have these kind of quantized levels like we did before. Now one thing that's curious is that actually the protons and the neutrons we deal with separately in the nucleus. And another thing which is different is that, remember, where the electrons tend to spin, given a choice, we think about this with electrons in boxes, spinning parallel in different orbitals, we actually find the opposite is true in the nucleus, because we've got this additional new fundamental force of nature, the nuclear strong force, which really holds the nucleons together. Electrons actually will, protons or neutrons will preferentially pair with each other because, rather than just repelling electrostatically, they also have this very strong nuclear strong force holding them together. So it's like a whole new kind of ball game in a way, what's going on in the nucleus. And but actually, when in NMR we do need to know what nuclear spins are when we're doing the experiment, and in fact this is actually could be worked out by considering protons and neutrons separately. And an interesting one actually is deuterium. So of course this is heavy hydrogen, where you've got a proton and a neutron in the nucleus. And of course we use deuterium in proton NMR when we want to make hydrogen invisible. So for example, if you've got a solvent in which your sample is dissolved, you want your solvent to be invisible in the spectrum, because there's so much more of the solvent in the sample, it would swamp the sample otherwise. And so typically in proton NMR, we deuterate the solvent. So the solvent doesn't contain any normal hydrogen, it's been replaced by deuterium. Because the deuterium, its resonance will be invisible in a hydrogen spectrum. The only thing that would be visible would be coupling with the deuterium from another nucleus, with a hydrogen nucleus. But this is interesting, you see, because in the case of deuterium, you've got the spin half proton together with the spin half neutron. And so actually the deuterium, that heavy hydrogen nucleus, actually has a spin quantum number of 1. So the capital S is 1 for those two nucleons added together, and we can observe this in NMR. So actually carbon NMR is an interesting case. So in carbon NMR, if for example you're working in the solvent of deuterochloroform, CdCl3, which is a very common solvent, of course we can make the hydrogen in that solvent invisible, if you like, in a hydrogen NMR spectrum. But when you're doing a carbon-13 NMR spectrum, then really there's no hiding it. So if we had a molecule CHCl3 and we were doing carbon-13 NMR, then 1.1% of the carbons in the chloroform, if they were coupling with a hydrogen, then you'd actually see that carbon-13 peak split into a doublet. This is the n+1 rule in NMR. But the curious thing is that when you're working with deuterochloroform, in fact, just to remind you, the reason why in CHCl3 the carbon-13 line would appear as a doublet is because half of the H's will be spin up and half of the H's will be spin down. And so the spin up or spin downness of the hydrogen is like a little perturbation on the magnetic field experienced by the carbon-13, and that's why the carbon-13 will be in two very slightly different magnetic environments, which is why you see two different peaks in the signal of the doublet. But the curious thing is that when you change the hydrogen for the deuterium, because now the total spin number quantum number is 1 rather than a half, rather than just having two possible spin states, up and down, plus half and minus a half, you've now got three possible spin states, plus 1, 0 and minus 1. And so because there are now three possible spin states, and at sort of thermal temperatures, we expect all of them to be sort of equally likely to be observed, we actually observe all three in the form of the carbon-13 signal being split into a triplet. And it's a 1-to-1-to-1 triplet, which represents the fact that the three spin states of deuterium will be equally likely, 1, 0 and minus 1. Whereas, of course, the other time you see a triplet would be, of course, if you are coupling with, say, two protons. And that would be a 1-to-2-to-1 triplet. And this reflects the fact that, you know, you've got the different possibilities of up and down. So you've got like an up-down and a down-up combined together to make that middle peak twice as large. So there you go. That's another interesting so curiosity there of that particular business of spin, how the nucleus can have a slightly larger spin than a half, for example in hydrogen, when you put a neutron in the nucleus as well to give a total spin of 1, and how this is manifest in the NMR experiment with the carbon-13 coupling with it. And actually you can see on the screen here, just got a little example here of a CdCl3 in a carbon NMR spectrum, so that's the ppm scale at the bottom there. And so it's around about 78 ppm, you see this carbon-13 peak coming out as 3, 1-to-1-to-1 triplet. So that's a nice curiosity there, all part of the story of spin as we see it in one form or another.